There we go. So now we're going to begin our discussion of Chapter 7, Reactions in Aqueous Solutions, but there's really more to it than that. We're going to extend our talk of stoichiometry and determining masses that react to produce masses as products, and how you use the balanced equation to determine those conversions. And then we will talk about reactions in aqueous solution. We may not get to that today in much detail, but that's okay because we've got plenty of time. We can finish it up next time we meet. So, what drives a chemical reaction? Did that thought ever occur to you? Just because you put two reactants together doesn't mean they're going to do anything, right? You could consider the air that you breathe as a mixture of reactants, oxygen, nitrogen, a little bit of argon. But they don't react, do they? The answer is no. They don't react. Not as they are in this solution that we breathe day in and day out. The only time you get a reaction out of any of them is when you provide some push to make them react. So there are driving forces behind chemical reactions, what makes them go. And these are the most common, the four driving forces that we're concerned with. If you see a solid form, then that will drive a reaction. Think of it this way. If you have reactants that produce, let's say, one product here and another product there, but one of them is a solid and the other remains in solution, how about that? Then what's going to happen? Well, when you produce that solid, it's going to drop out of solution. It may not happen right away, but it says that any of these reactants that were in aqueous solution over here prefer to be solids. And this is a qualitative description. This is not quantitative. You want a quantitative description of these driving forces, you have to take CHEM 1 and 2. Okay? These are qualitative descriptions. So if you form a solid, that drives the reaction that direction, because it's essentially removing itself from the environment. And if you do that, if you remove something from an environment, it can't react anymore, right? So it tends to run things, think of it downhill to the solid, like that. That drives the reaction. Formation of water will also do that. The most common reaction that forms water is an acid and a base. Acids and bases, when you put them together, will react, and one of the products is water. That drives the reaction. If you get a transfer of electrons, the reaction will be driven to the other side. And that reaction has a special name. We'll define it in more detail later, but it's called redox reaction, when electrons are transferred. Such as when you connect the terminals of a battery, electrons are being transferred. And that is a push for the electrons to move, to go from one place to another. To complete the reaction, we separate the reaction in such a way that we can access those moving electrons. That's why the terminals, unconnected, you don't get a reaction. And your batteries can, many of them sit for years and remain fully charged. But once you connect the terminals, you provide an avenue for those electrons to move from one side to the other and react. And then the formation of a gas. In my mind, this is the easiest one to understand. If you form a gas in the reaction of if your reactants form a gas, then where does it go? It removes itself from the reaction environment, just bubbles out. So if it's going that way, then it's like it leaves a hole here, and more has to be formed to fill that void as the gas is removed from the reaction environment. Okay, that's the way I think of it. So those are 4 driving forces for reactions. There are others, but these are the 4 most common. If you form a solid, if you make water, if you transfer electrons, or if you make a gas in a reaction, that will drive the reaction. It's also, well, you can see some of them. Forming a solid, forming a gas, you can see those as physical evidence of reactions occurring. The others, this takes a little imagination. This one you can actually measure the movement of electrons. I may have to quickly get it started.
So in the reactions we've seen so far then, we mix chemicals together and we know that a reaction has taken place because we get a change of colour. There are lots of other ways that a chemical reaction can show up. And one way is called a change of state. So the state of something just means whether it's a solid or liquid or a gas. So something turns from a solid to a liquid or from a gas to a solid, then it's a changed state. So let me show you an example of a chemical reaction that involves a change of state.
Not around here.
So I'm going to use these 2 liquids, and a red liquid and a colourless liquid. What I'm going to do is to pour the colourless liquid onto the red liquid very carefully and try to make 2 layers. What I want to happen is for the colourless liquid to be floating on top of the red liquid in separate layers so they don't mix. It's worked quite well. So what I've got now is one liquid floating on top of another, and where they meet, they undergo a chemical reaction. I'm actually making a solid. A solid material is formed where the 2 liquids meet. What I can do is to fetch out some of this solid material. And as I pull it out of the beaker, of course, it allows the 2 liquids to meet each other again, and so they react again to form more of this solid. If I'm careful, so as I wind, I'm pulling up this material, and it allows the 2 liquids to meet again, and it forms more of this material. And this substance that's being formed is actually nylon. So we're making nylon as I speak. And if I'm careful, I'd be able to just keep on turning this and making this long thread of nylon, at least until we run out of solutions. Okay, so that's an example then of a chemical reaction that involves a change of state. Let's have a look at another reaction that involves a change of state. And for this, I'd like a volunteer, please. Who would like to volunteer? You're very keen. Come on down. Let's have a big hand for our volunteer. Who would like to stand there? Let's pop those on. What's your name? Dylan. All right, Dylan, if you stand just there, we're going to do some chemistry. We're going to make it a solid. All right, I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. When I add the ammonia, you see that it's forming a sort of brown colour. You keep on adding the ammonia. In a minute, that brown colour should disappear. Oh, that's disappeared, isn't it? Now what I'm going to do is add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So now I'm going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. 2. There we go. And then finally, I'm going to add some glucose. So there's the glucose. I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan. I want you to hold that. Now to give a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place and it's forming a solid. The actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works. So keep shaking, don't drop with that. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the sort of a mirror building up on the inside of the flask. And you'll all have seen those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. Little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, so have a quick look. Almost there, keep going a little bit longer. So looking a little bit dark. Excellent. All right, give it back to me then. Right, we're going to take the clip off. Take out the stopper. Let's wash that off. And we'll pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. And rinse it out a second time. Rinse it out a third time. There we go. Just look at that on. Let's dry this off. Put the clip back on. And if we like to just give that a little polish, so if we like to hold that up behind the neck, that's it. If we bring a camera in, have a look at this, and we've got a lovely silver mirror. There we go. Okay, what we're going to do is give that to you as a souvenir to take home, and you can go back to your seat. Let's have a handful of it. Okay, so that's an example of a chemical reaction that produces a change of state. I want to show you another example of a chemical reaction. Again, this is going to go from being a liquid to being a solid. So in this flask, I have a solution of sodium acetate. And this sodium acetate is a liquid, as you can see, but it would very much like to be a solid. It would like to turn into a crystal. And it needs a sort of an excuse to get going. And the excuse is going to be some little crystals of solid sodium acetate in this dish. Watch what happens. I pour the liquid onto the crystals. I think you can see there the liquid, as soon as it touches the crystals, it's turning into a solid. And with a bit of luck, we can make a sort of chemical sculpture. Seems to be working. Okay, so that's a sort of sodium acetate sculpture. Now, oddly enough, this actually has a practical application. This is the practical application. This is something called a hand warmer, and it's a plastic pouch, and it contains exactly the same liquid as in this flask. It's a solution of sodium acetate, and it would like to turn into a solid, like to turn into a crystal, but it needs an excuse to get going. And the excuse is this little metal disc, and if I just flip this disc backwards and forwards, that should be enough just to start the crystallization off, and there it is. And you can see the liquid turning into a solid. And as it does so, it's actually getting warm. It's actually giving off heat. And there it is, it's turned entirely into crystals. It's become quite warm in the process. I can put that inside my glove and keep my hands warm for half an hour or so. And then I can take this and put it into boiling water for a couple of minutes. The crystals will turn back into a liquid. I can allow it to cool and then stay as a liquid. It'll stay like that for weeks or months until I'm ready to use it again. We can use it thousands of times. Okay, so that's sodium acetate, a sort of chemical sculpture. I'm going to show you now another way to make a chemical sculpture. And Chris has been preparing this. This beaker contains a mixture of para-nitroacetaldehyde and sulfuric acid. And Chris has been warming it up. And when it's hot enough, it will undergo a reaction in which this liquid will turn into a solid. This makes quite a bit of smoke, so we've got this special hood that will suck away the smoke from the reaction. Here it goes. Okay, so that's the chemical reaction that involves a change of state. So
You can do a similar reaction like that, only you don't have to heat it up. You can use table sugar and concentrated sulfuric acid. Both together, it'll produce that black chimney. But it'll do it immediately. So this way, you have some control over the reaction. Okay, we've got a few more minutes. So let's see what other mischief we can cause. Here was the example we gave earlier where a solid was formed. This reaction is called precipitation. So when you add two liquids together and the reaction produces a solid, we call that a precipitate. So the reaction is a precipitation reaction.
What I have here is two preliminary flasks. One has lead nitrate solids at the bottom, and one has potassium iodide solid, or salts in the bottom. I'm going to make a solution, aqueous solution with these. So I have aqueous lead nitrate here. Mix in.
Oops.
You can see that it makes a solution. It does dissolve. It is definitely aqueous. And same thing with the potassium iodide. Hopefully I don't make as much of a mess. It's the Ki, adding some water. Also make it an aqueous solution. And both of these solutions, or both of these salts, are soluble in water. So let's stir. And I have two aqueous solutions. You can see through them, and you can see the solids are now been dissolved. Okay. Now, interesting enough, lead nitrate is made of the nitrate ion. Nitrate ion is NO3 minus 1. Anything combined with the nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a negative 1 stretched over 4 atoms, so its charge density is very low. So it doesn't attract other ions in a crystal as strong as others. So the lattice energy is lower, and it's easy for water to pull apart the ion and have those molecular ion attractions that make this a possibility. Same with Ki. You have potassium iodide. You have Ki ions that are free. This aqueous solution, and the K is +1. The +1 ions are a big ion, and they are spectators for most types of reactions because they have a +1 over a large area as well. And the iodines, like most halides, are also soluble because they're negative ones, also a big ion. Some exception to those. You can see that one right here. So I pull 4 of these together and take 2 aqueous solutions and see if they precipitate results. Precipitate is when a solid comes out of the solution because we're going to do a double replacement, which people have metathesis reaction. Lead +2 from this beaker is going to attract and hook up with the iodine ion to make PbI2 or lead-2 iodide. And that is going to create a precipitate because the lead iodine prefers itself more or attract itself more than water. So let's do that. Here we go.
Before he does that, he used some terms in there, and the only one that you really need to be interested in is double replacement. So here are your compounds: lead nitrate, potassium iodide. That's because lead has a 2+ charge, and nitrate has a 1- charge, so they're balanced that way. And here you have a +1 and a -1, so they're balanced. So what he means by double replacement is that this one replaces the potassium in that compound, and this one comes over here to replace that one. You can think of it as these swap, potassium and lead swap places. And what you get is, I'm going to have to draw it down here. You get potassium combined with nitrate. Which stays in solution. And lead combined with iodine. And that forms your solid. So let's watch what happens.
So, very brilliant reaction. You see that pretty, very pretty yellow precipitate.
There's your yellow precipitate.
Yellow lead paints have been known to be yellow. Also a problem. So there you go, there's a precipitate. And it's a precipitate because I know that I cannot see through the solution. And if you let this settle for a while, we get something like this. This is a reaction I did about an hour or so ago. And you can see here that the clear solution is the potassium nitrate ions, and the solids are at the bottom. That's settled at the bottom. All right. So there is your precipitating reaction.
Okay. Let me see where we're headed with this. Find a convenient place to stop. This might be a good place. Let me make myself a note, and we'll pick it up here on Tuesday. Tuesday, the 31.
There's a lot of other days.
First day would be 10-1 then, really. Yep. We'll come back on the first day of October and finish this discussion. And in the meantime, you can start looking at that review document. If there's anything in there that if you run across a problem that we haven't covered yet, just skip over it. There's no sense in wasting your time unless you're just super curious and have the time and the energy. Go ahead. I'm not going to hold anybody back. Okay, so that was part 1. We'll pick up part 2 on October 1st. Right. History is a new teacher. They'll be along in a little bit.
Do you have a class after this?
No. You want to make up an exam?
Well, I can't make it up then, like right after this class, because I have another class. And then I have to go to financial aid.
I'm good till, well, let's see, I got to give you enough time to take it. If you come by 11, can you make it by 11?
No, my class ends at 11.
At 11, okay.
Well, it's at 10:45, but I can't take a test.
Okay. Tomorrow is Wednesday. Let's see. Wednesdays. Are you going to be here on Wednesday?
Yes, I have a class 9:30 to 11.
Till 11. Okay. Well, that'd be good. How about 1:30?
Yeah, that should be fine.
Okay. I'm going to put you in here so I won't forget to. Yeah, that's not the one. Okay. Okay. I need to label the boards so the video will know what we're talking about. Did green show up? Yep. And this is Exam4. And Chapter 7 on team. Okay. So we had just dipped our toes into Chapter 7 last time, talking about the driving forces behind reactions and seeing this video. And then we're starting to look at the various things that can be considered driving forces for a reaction. One of those is precipitation. If you form a solid as a product of a reaction, it tends to drive the production of that solid. We call the solid a precipitate. We saw that one too, didn't we? we didn't need to watch that again. Okay, aqueous solutions. What we mean by aqueous solutions is just that the solvent is water, and the solute, that is whatever is dissolved in the solvent, is something else. Whatever is compatible with water, whatever will be attracted to the water molecules and enter into solution. When we form those solids, the precipitate is not attracted to the water. So it tends to drop out of solution, we say. But there are characteristics about water that when you take a closer look at them, they help you understand why water is attracted to some substances and not attracted to others. Okay? Water is often referred to as the universal solvent. That's kind of a stretch. It does dissolve a lot of things, and some of them more than others. Some is like excessively soluble in water, like table sugar. You can start off with just a little bit of sugar in your water, keep adding it, keep adding it. You'll eventually reach a point where there's a whole lot more sugar in the water than there is water. And there are other things that will just refuse to go into solution, like oil. And you try to anybody make their own salad dressing in here? No. I use those little armored chipped beef containers. They're about that big around, and they have a little snap cap on it. Pull them off, and you chop them up and make SOS out of it. I clean those up, and they're just the perfect size for one salad. So you put however much oil in there you want, vinegar, and then you add some seasoning. Mrs. Dash is easy. And then you just shake the hell out of it. Try to get it to emulsify, we say. And then you pour it on your salad as quick as possible, because within a few seconds, it's going to start to separate. So you get it on your salad before it does that. Well, oil and water don't mix, they say. Right? So there's a reason for that. It has to do with the nature of water. So water is a polar molecule. So I probably ought to define that term. What do we mean by polar? Well, if you look at representation of a magnet, right? A magnet has a north pole and a south pole. And you know how it behaves when it gets around other magnets, right? If you put it next to another magnet like this, what kind of forces will it feel? Repulsion, right? They'll push when you get these two together. If we flip it around, let's see, this is repulsion, like that. But if you put a magnet on this side, south and north, you'll get attraction. Okay, that's a concept of polarity. That end is different than this end. So when we talk about polarity of a molecule, we're talking about distribution of electrons in that molecule. So you would get maybe positives, more electron density over here. This is one way of drawing it like that. Okay. So you get more electron density over here in that side of the molecule than in this side. So then if you have two molecules come together and they approach close enough, the positive of one tends to attract to the negative of the other. That's how you measure polarity, is how strong is that attraction. So then, once we understand what polarity is, how do you tell if a molecule is polar or nonpolar? That is, a nonpolar will have a relatively even distribution of electrons throughout the molecule. There won't be an offset of any major amount, one side or the other of the molecule. So that one would be considered nonpolar. But if we have a molecule that naturally wants to redistribute the electrons in one section, and that makes the other section more positive, then you get polarity. The water is just like that. Right, there's the formula for water. You have 2 hydrogens and 1 oxygen. But if we draw it like this, then we find out that based upon how strongly an atom wants to attract electrons, there's a difference between this one and that one. They're bound, they share electrons, but oxygen has a much stronger pull on electrons than hydrogen does. We're going to get to that in a second. This is just we're talking about now polarity of the bonds themselves. Okay? So you can speak of polarity in terms of individual bonds, and that's what we're doing here. So we draw it like that, showing this as the positive end and this is the negative end. And there's a draw on electrons toward the oxygen, right? So that gives you a negative distribution there and a positive one there. To balance them, we'll put a 2 there. So that delta is a Greek letter that we use to designate a slight distribution of charge, as opposed to an ion, like this. In that case, this sodium has lost an electron. I mean, it's completely gone, makes the ion. But in this case, the electrons have only moved this direction a little bit. So that doesn't give you a complete charge here. It only gives you a slight charge. That's what the delta means. Slight positive, slight negative. Now, if this is the case, then this one drawn that way and this one drawn that way, they cancel one another out because that arrow is going this way and that arrow is going that way. So this would be a nonpolar molecule based upon its geometry. And now we get to your point. Water is actually bent like this. So that same bond polarity is now additive. They're both going that direction in general. So when we add them together, we get an overall polarity like that for the molecule. So that means that overall, the distribution of electrons is like this, like that. So the water molecule has a positive side and a negative side.
That's, I guess, the concept of where you get the shape from the stick graphs.
Say again?
Is that where you get the concept of like the shapes of the stick graphs? We look at it.
Yeah, right. 2 things determine the polarity of a molecule. First, does it have polar bonds? And then, what is its shape? If the polar bonds are opposite one another, they cancel out. So the molecule overall is nonpolar. But if the shape gives you an offset so that you can add them together and get a distribution of negative one side, positive the other, then you have a polar molecule.
So the left side's polar, the right side's not. I guess with the power.
Now the top side, oh yeah, I see, yeah, that's polar, this is nonpolar, but that's not real.
Right.
Right? That's not water, this is water. And we've got some stuff up here to sort of illustrate it. So what does that do for water? If you only have, before we put anything in water, how does that affect the behavior of water? You've got nothing but water molecules. It's a pure substance. So if you have these waters in here, how are they going to orient themselves? Well, the positive to the negative, right? Like that. So this negative is attracted to that positive. okay? And individually, this bond is much, much weaker than the one that holds the molecule together. But overall, you've got billions of these interactions going on at any one time. And they together add up enough force to hold water together. So at this temperature, and this pressure, atmospheric pressure, room temperature, so to speak. Why is it doing that? Is it still recording? All right. So let's pick up where we left off. The polarity of the water molecules is due to two things. The polarity of the bonds, the individual bonds, and then the shape of the molecule. If the bonds are opposite one another, they'll cancel, or if they're in the form of a symmetrical design, like a tetrahedron, such as, here's my green, such as, everybody knows carbon tetrachloride. No, maybe you don't. They used to use it as a dry cleaning fluid until the EPA and OSHA said you can't use it anymore because it's making your workers sick. But carbon tetrachloride has a shape like this, chlorine with carbon in the middle, and that one is in the back. So we get this triangular arrangement here, and in space, it's a tetrahedron, regular space. Well, the polarity of these bonds is like that, every one of them. But because they're spaced regularly around the molecule, they cancel one another out. So carbon tetrachloride has polar bonds, but the molecule is nonpolar. So that's why it's so volatile at room temperature. And that brings us back to water. The nature of water at room temperature is it's a liquid, and it's not very volatile because of these bonds that hold it together. It takes a lot more energy, higher temperature, to break those bonds and turn it into steam. That's why water has such a high specific heat capacity. It can absorb a lot of heat before it even turns to steam, right? From zero ice where it melts up to 100 degrees. It's got that wide range, temperature range, which is why the climate on Earth is really very stable, because we've got so much water. They don't call it the water planet for nothing. If it weren't for this characteristic, if water were like, well, the other one where it was flat, it would be at this temperature, it would be a vapor. We'd have no liquid water on the surface of the Earth. Okay, we probably wouldn't be here either. Okay, so how does that affect the way water behaves as a solvent? Let's see. I'm going to look ahead just a few steps. I feel like we've defined solvent and solute, have we? I'll say it again. The solvent is usually the major component. That is, what do you have first that you're going to put something into? That's the solvent. The solute is what you put into it and try to form the solution. Now, I know we've defined solution. It's a homogeneous mixture. Everywhere you look, you see the same composition, the same amount of your solute for every given amount of the solvent. A heterogeneous mixture would be something like soil or a jar of jelly beans. You know, you don't see the same composition wherever you look. So our solution has those characteristics. It has a solvent, it has a solute. And when we say aqueous solution, we are designating water as the solvent. So learning something about the solvent behavior tells us what we can expect to be soluble. What solute will go into solution in water. And I don't know if you've heard this before, but like dissolves like. Polar solutes dissolve in polar solvents more readily than in nonpolar solvents. So nonpolar solvents will dissolve nonpolar solutes relatively easily. Okay, it's just a rule of thumb. So anything that is polar is likely to go into solution. That doesn't guarantee it. For instance, when we produce those precipitates are formed from ions that come together. But just because they're ionic doesn't mean that their positive and negatives will be attracted enough to the polar water to put them in solution. There are other forces involved. But a first step says that you're more likely to get ionic substances or polar substances to go into aqueous solution. So what are some examples of solutes that will go into solution? Well, a couple come to mind. Table salt. Table salt goes into solution as sodium ions and chloride ions. So what happens is the water molecule approaches the crystal of sodium and chlorine. And in this matrix, these are separate ions. Like that. In that crystal. Have you ever looked at spilled salt on the table and looked at it with a magnifying glass? No? It forms little cubes, little tiny cubes. And these cubes are the regular arrangement of sodium and chlorine ions in that matrix. If you put it in water, then the water molecule approaches, and when it approaches a positive and presents the negative side, right, there's an attraction there. But it's not just this attraction, because this one is attracted to other water molecules, right? So they're pulling like this. And eventually there's enough force to dislodge that sodium ion. And the more it comes away from the crystal, the more available it is for more water molecules to come in and form bonds and pull it further. So once you get started, it's inevitable. That sodium just goes. We call that process of solvation, or in this particular case, hydration, because the solvent is water. Now, some ionic compounds resist that so much that they remain solid even in water. So that's where we get that concept of precipitation. If the strength of the bonds holding the crystal together are stronger than the forces trying to pull them apart, then they'll remain solid and just fall out of solution. We'll talk about those in particular later. But the polarity of water is what makes it attractive to ionic or other polar substances. Right? So this was the case of an ionic substance being attracted and solvated by water. There are other possibilities where you don't have to tear the molecule apart or tear the crystal apart. Table sugar was one that I mentioned before. All right, so let's keep it simpler than that. Table sugar is a disaccharide. In other words, it's actually two sugars hooked together. Well, the one sugar that's important to human metabolism is glucose, right? If you got too much glucose in your blood, you're diabetic. Right? So you want to control it. Your body has complex mechanisms for controlling the amount of glucose that's in your blood. Well, the glucose molecule itself, it forms a ring. And wherever these things meet, that's a carbon. Okay, we just don't draw the carbons in there. It takes up too much space. Right, so each one of these is a carbon, except for when we show it's not. So there's an oxygen there. Okay? There's also a carbon up here. 2OH. Okay. All around this molecule, there are alcohol groups, hydroxyls, just like that. Okay, so what do we get from that? We get these bonds right here, these individual bonds they have their own polarities, right? So the hydrogen is going to be slightly positive and the oxygen is slightly negative. So whenever water approaches, it's going to form, just like before, form that bond. But look at all of them. It's got ample opportunity to form all kinds of bonds with this molecule, simply because of all these polar bonds around here. So that's why sugar goes into solution rapidly and in large quantities. Okay. In fact, my master's degree is in food science. And one of the things we studied was, how do you get foods from one place to another, or processing components, things that you use to process foods, right? Sometimes you take them from one place to another as a solid, in packages. It's very inefficient. More efficiently, if you can send them in large tanker trucks or on rail cars, right? And one way they transport sugar, table sugar, this is glucose, but table sugar just has another molecule out here. So the concept is similar. So sucrose, you just put it in solution, and it's so soluble, it only takes a little bit of water to make your sugar solution, and you just pump it into a tanker, either on wheels or on rails, and then ship it to location. And then you just pump it out. And if you need to remove the water, there's not much water there. It's simple. You just add a little energy, boil off the water, and you're ready to go. That's just a practical application of sugar solubility. So that's what it does. It surrounds the polar substance and pulls it into solution. This is an animation of what I was describing earlier. So here come the water molecules. They're approaching the sodium. That's a process of solvation. So they can do the same thing to the chlorine. But in the case of the chlorine, you get the positive side attracted to the negative. Here you have the negative side attracted to the positive. Okay. So another characteristic of water, since water is non-ionic, it does not form sufficient ions to conduct an electric current through itself. So that makes pure water an insulator. But if you put something in it, dissolve something in it like sodium chloride, you have those free ions floating around. They may be solvated, but all you need is a little bit of push from one electrode to the other, and they move. And that carries the charge through from one electrode to the other. That makes some solutions conductors. But in order to be a conductor, you need ions, free ions, not this slight charge thing. It has to be a complete ion. So if you put something ionic in solution, it will allow you to conduct electricity through water. Those are called electrolytes. You've probably seen electrolytes on your medical report. When they do a blood test, they do a whole panel of electrolytes. Those are the things that form ions in your blood, like sodium and chlorine, potassium, calcium, magnesium. They're mostly these guys over here, and a few of these, maybe chlorine. Perhaps iodine, since iodine is essential. But those are the electrolytes. And they're called electrolytes. This is operationally defined, they say. Electrolyte is anything that goes into solution and conducts electricity. Now, another extension of that definition is strong versus weak electrolytes. So a strong electrolyte will light up your bulb really bright. There's virtually no resistance in the solution with a strong electrolyte. Whereas a weak electrolyte will only light your bulb up weakly. You know, they're not going to show us. But it wouldn't be as bright. And what that means is, in terms of what does the molecule do, for sodium chloride, when it goes into solution, it goes completely into solution. Everything here ends up there in aqueous solution. Whereas a weak electrolyte, like vinegar, acetic acid, C2H3O2. Vinegar dissociates into this, right? The acetate ion and hydrogen ions, that makes it an acid, right? But whereas we can put one arrow here and that says everything that direction. This one goes like that, but like this. It's mostly over here. So it only dissociates a little bit, but it's enough to conduct some electricity. Okay, the difference between a strong electrolyte and a weak electrolyte is the amount of dissociation when you put it in solution. Okay, so here's an example of a reaction between these two compounds. First, we put this one in solution. Everybody know what that's called? That's a polyatomic ion, right? It's the chromate ion. And it has a 2- charge, so it will be neutralized with 2 1+ charges. So that's why K2CrO4 is its formula. But it will go into solution, and when it does, it forms these individual ions. And everything goes into solution. It's like sodium chloride. All of it goes into solution, separates into those ions, and is hydrated by the water molecules. Same thing happens for barium nitrate, right? Barium dissociates, nitrate dissociates, they're in solution. So once they're in solution, if you put them together, like we saw in that previous video, where the guy had these two solutions and he put them together, these compounds are actually not the ones that interact, because in solution they're individual ions. So you have the opportunity for this positive to interact with that negative, now that they're put together. Before, they didn't have the opportunity because they were in separate vessels. But once you pour them together, this one can interact with that one, and then this one from that jar can interact with this one from that jar. So that's where you get a reaction we call a double replacement. Okay. It just means these positives swap places with each other, and you get some interaction between a new anion. At that point, then you have to ask yourself, well, what are they going to do when they interact? All right? Are they more attracted to water than they are to each other? In which case, they just stay in solution. That's the case for potassium and nitrate. They are more attracted as individual ions to water than they are attracted to one another. So they remain in solution. Nothing happens. But the barium and the chromate are very strongly attracted to one another, much stronger than they are to the water molecules. So when barium and chromate interact, they form a solid, and they drop out of solution. That's your precipitate. They like each other more than they like water. That's one way of thinking of it. This is another way to do interactions. If you have these individual ions here and here, what are the possible interactions? Once you put them all together, well, the potassium can interact with nitrate, or it can interact with chromate. Barium can interact with nitrate, and it can interact with chromate. And then you look at each one of them, and you see whether they're soluble or not. And I have a chart, I think. It's probably in that review document. Yeah, here it is. It looks like this, right there, with clear squares and gray squares. Down one side, here are the anions, the negative ions, and the positive ions across here. So it's kind of like reading a road map, you know, distance from one place to the other. You follow this one out until it meets the one coming down. The negative meets the positive, and you look at the square. If the square is gray, then their interaction makes an insoluble product or precipitate. It drops out of solution. If it's clear, then they stay in solution. Okay? This is the simpler way to deal with solubility. There are a set of rules down here, and if this were a general, actually I don't even do it for my general chemistry class. But if I were teaching chemistry where the programs of my students were to actually go and be chemists somewhere, go on to bachelor's degrees and further, I'd have you memorize those rules, right, rather than use the chart. But since most of my students are going into limited access chemistry, chemistry is only part of their program, then I just let you use this chart. And it's easy to find out if the product is soluble. You just have to learn how to use it. And if you use it enough, you sort of figure out these rules on your own anyway. Okay, back to the topic. So what are the products? So these are the reactants. And the possible combinations are, like I said before, potassium and nitrate, potassium here, nitrate there. And then you look at the chart and you find out, well, potassium nitrate, before you put it in solution, would be a white solid. But once you put it in solution, it's only a white solid if you evaporate all the water. But as long as it's in the water, you can't tell, it's dissolved, right? But barium chromate forms a yellow solid, even in the solution, because it's insoluble in water at that point. This is the case where you have ions that you put in water, but they're not necessarily soluble. Right? We expect ions to be soluble in a polar solvent like water. But in this case, I had one professor say it ain't necessarily so. Right?
3 stars.
3 stars? Yeah, there's some, what does that mean? Okay.
Almost.
Yeah, so it's soluble, but it's not soluble as the compound that you put in water. If you take, for example, if you take sodium oxide, that's a solid, but if you put it in water, it doesn't just dissolve, it becomes sodium and oxygen in solution. Right? It actually reacts with the water molecule and produces sodium hydroxide. It produces a base. Now the base is soluble. Right? You can get sodium hydroxide. I think you can still get it as a solid in the hardware stores. Lye, solid lye pellets, right? Used to be marketed as Drano. Right? Now, instead of pouring solid Drano down your drain to clean it out, they put it in a liquid plumber. Right? They make a solution out of it, and then they put a thickening agent in it, so that it'll hold together and drop into your drain even through standing water and dissolve out the hair and the organics that are clogging the drain. And I guess they figure it's safer to use that way too, rather than the solid sodium hydroxide that used to be in these little cans. I don't know if you can still find them or not. I haven't looked lately. But this then is in solution. I don't think that's balanced yet. There's 2 sodiums. Is that balanced? 2 sodiums, 2 oxygens, and 2 hydrogens. There you go. Okay. So that's what those 3 stars mean. These oxides react with water to form a base. But the base is soluble. That's why that block is still clear. Because it's soluble, but it's not soluble as sodium and oxygen ions. It's soluble as sodium hydroxide because of the reaction. Okay. So where are we going with this one? Talking about solubility. Now these are the rules for solubility, and I'm not going to make you memorize it. But if you ever use them, they're in order for a reason. Right? Yeah, all nitrates are soluble. Most sodium, potassium, and ammonium compounds are soluble. Sodium and potassium means these guys right here. In fact, most alkali metals compounds are soluble. But there are exceptions. And we get to the exceptions down here. Right? Most chlorides are soluble, except for silver, lead, and mercury 1. They're in order like this, so that if you have a compound that you're trying to decide whether it's soluble or not, then you look down here and say, okay, it fits right there, but maybe the cation fits here and the anion fits up here. If there's a conflict between one down here, one up here, the one above wins. Right? The one above takes precedence. That's how you break a tie. But you probably won't care anyway because I'm not making you memorize it. Now, there is a distinction to be made between soluble, insoluble, and slightly soluble. Because most compounds in solution, even though we call them insoluble, they're really slightly soluble. In other words, what was that? Barium chromate? Yeah, barium chromate. Is insoluble. We've said it's insoluble in water, but in fact, it does dissociate very slightly in water. The vast majority of it is over here. But just a few ions are in solution. So that's what we mean by slightly soluble. And if you were taking my CHEM1 class, we would calculate that value. You'd be able to tell exactly how much is in solution with this compound because there are constant values that are associated with it. Okay. But we're not going to get into that in this class. I'm just making the point that there's soluble and then there's soluble. So there's your chart. Here's all the rules on it. But you only need to know how to use this one. So when you find a compound that the question is it soluble? You've got to know which is the cation, which is the anion, then find out where they meet. And then you can tell whether they're soluble in general terms. Okay? This is more discussion of solubility. Oops, let me back up. If it'll let me. I might have to take control from here. It's not going to let me. It can't be that way. Go back, back. Go back to this one and start over. There we go. So, when you mix two solutions, and we're trying to determine if we have a precipitation process form that's solid, you write out the reactants on one side, and then you do that double replacement dance, right? So the example we had before was let's see, barium nitrate. Yeah. Barium nitrate is soluble. If you go back and look at the rules, you find all nitrates are soluble. You can look it up in your chart and find the same, draw the same conclusion. Potassium chromate is soluble because most potassium salts are soluble. That's the rule that applies. These go into solution, and then how do you know what the reaction is? In most cases, you have to be told what the products are in a reaction. But in the case where you have a double replacement like this, you can predict what products will form. Potassium is now available. We write it like this. Potassium is now available to interact with nitrates, right? So we get potassium nitrate. And we look it up and find that it's soluble. In fact, it's a double whammy. Potassium salts, sodium and nitrate salts, they're all soluble. So that guarantees solubility for potassium nitrate. And then the other possibility is barium ions plus the chromate ions. They interact. And then you look at your chart, you find the barium on one side. Not going to let me go back. You find the barium, look for it across the top, chromate down the side, and you find out where they meet, and it should be grayed out. Right? So this forms a solid. That's your precipitate. Okay? Then you just balance it like any other equation. You be sure that you've written this correctly, +1 - 1. plus 2 minus 2. Those are written correctly. Then you balance it. That's it. That's all it takes to balance that equation. Okay? So now you've got your overall, this is the molecular equation. Right? Because we've written it as if they were molecules. But the truth is, they're not. In solution, they're individual ions. So this one would be like that, right? 2 potassiums in solution, 1 chromate in solution, 1 barium in solution, and 2 nitrates. Squeezed too close together. In solution. That's what actually goes on here, this part. Those are in solution before the reaction takes place, right? Because they're soluble. That's what we mean by aqueous. Then what happens over here? Well, now you have 2 potassiums that are in solution still, and 2 nitrates that are in solution. Okay? But this one, I might have to write it down here. This one's a solid. You can't change it. Right? It doesn't, it's not in solution, it's a solid. So you have to write it as a compound. This is what's called the complete ionic equation. This is molecular equation. Okay? This is the true story. These are all the ions that go into the reaction. These are the ions and solids, if necessary, that come out. Those are the products. Okay? So what do we know about writing a chemical equation? If you've got the same thing on both sides, it's valid to cancel them out. Because they're not doing anything. They're really not part of the reaction. Right? We call them spectators. So we've got a spectator here because it's on that side and that side. And we've got a spectator here on that side and that side. So there's one of your spectators. And there's another one. Those spectators, if you cancel them out, because this one's on both sides, that one's on both sides, then what do you have left? This is the real meat of the reaction. You get that one plus that one yields the solid. That's the reaction. And this one is the net ionic equation. Okay? This is where the action occurs because you're changing phases from aqueous to solid. Whereas here, I mean, this is true. This is everything that's in the container, but this is where your attention is focused because that's the reaction of interest. Now, what's the value of writing it that way? That tells you, as a practical matter, if you don't have potassium chromate on your shelf, say you have sodium chromate, it's soluble, you know it's soluble, use it. Right? It'll work just as well because the sodium combined with the nitrate is soluble. And you can get that same reaction with a different starting compound. Okay, sometimes you have to do that. You don't have time to order the potassium chromate from the supply house and wait for 2 weeks, you know, while they go back in the back and search for it, you know, blow the dust off of it. Probably been sitting there for 3 years. Okay. Any questions so far? Let's see. All right, so this slide, I think we have a slide on that. We'll run out of time if I'm not careful. Yeah, we did get to that. I jumped ahead a few slides on this molecular complete net. It's in there. It just seemed like stream of consciousness fit better here. Okay, which of the following ions form compounds with lead 2+ that are generally soluble in water? Well, we're gonna have several to choose from. Let's see, we got another one. Yeah, we got another one. Which form compounds that are soluble? Well, for this one, you have your selection. You know, what possible anions are given to react with lead 2+. So you only have to go across the top of your chart, look for lead 2+ and go down. Say, where does each one meet? And see if it's soluble. Right? Of course, test taking technique. That one's out. you don't react a cation with a cation. So you really have to choose among these four. And then you look on your chart and you find that that's the only one that's soluble. The rest of them are insoluble. Okay. Most chlorides are soluble, except for those three that we mentioned, right? And lead's one of them. Silver's another. And what was it? Mercury? Mercury 1 is also insoluble, chloride. But we're dealing with lead here. So it's insoluble. Sulfate, lead sulfate is insoluble. Sulfide, excuse me. Lead sulfide is insoluble. Lead sulfate is insoluble. That's the only one that's soluble. So here's a word problem. We're going to react sodium phosphate with lead 2 nitrate, right? And it says they are solutions, right? That tells you that they are soluble, right? So what do you have to do? First thing you have to do is write the compound correctly. That's why I hammered nomenclature so hard. You've got to be able to write the compound. So sodium phosphate. Right? You know you have sodium, you know you have phosphate. But that's not written correctly. Because this has a 3- charge as a polyatomic ion, and this one only has a 1+. So you need 3 of them. And it's in solution. Okay, that's in one solution. We're going to dump it together with a different solution, lead 2 nitrate. So that tells you that this is a 2+ from the name, plus nitrate, which is a -1. You get that off of that list of polyatomics. So that means you need 2 of these. Since it's a polyatomic, you have to use parentheses. Now that we've written our compounds correctly, we can say, how are they going to react? Well, it's a double replacement. This one interacts with that one, and that one interacts with this one. Right? So let's start with the easy one. Sodium nitrate. That's a +1, -1. That's written correctly. We look it up, it's soluble. In fact, all sodium salts are soluble, all nitrate salts are soluble. So it's a double whammy again. It's guaranteed soluble. So we react lead with phosphate. Lead 2 with phosphate, 3-. So how do we get that one to balance? Cross multiply. 3 comes over here. 2 goes over there. Then we look it up on our chart. Lead, follow phosphate, and I guarantee it'll be gray. There's your solid. That's the precipitate that forms. Okay? Step by step. We build on what we learned before, hopefully. We learned our symbols, we learned how to write compounds correctly. Now we're reacting with them. Okay. A precipitate forms, it varies. It's still a solution. It's just clear, you see right through it. Right? If no precipitate forms, you see right through it. There's no, huh? Well, whatever color the solid is, lead phosphate, that's probably white. But when these solids form, they're extremely small particles. Like they're very small, finely divided. So initially, they just make the solution cloudy and may have a color. But if you let them sit long enough, it's like that video, they'll settle out. And he showed you one that settled for an hour. It was just a yellow powder sitting on the bottom of the flask. Some of them are brightly colored and some of them are just white. So let me see how much time we got to go here. Where do we go? 20 or 40? 40, good, okay. I'll start to panic. I want to be sure we get through all the major concepts. So I'm not going to spend a lot of time here. If you take that review document, you get a considerable amount of practice, in addition to the homework, actually. So if you have a chance, at least take a look at the review document. How many different solids will form? Okay, how do we decipher this mess? Well, you'll notice that some of them are anions and some of them are cations. So you know the cations are not going to interact. Only the anions are going to interact. So the simplest way is to set up a chart. Right? Just do this and do like your solubility chart. Put the cations across the top. So we got lead 2+, potassium, silver, and that's it for the cation. And down this side, we put our anions. And chloride, sulfate, and phosphate. Right? And then you go to each one of these where they interact and say, all right, are they soluble? Right? So we know that all nitrates are soluble. Soluble, soluble, soluble. Lead chloride, look that up. I think that's insoluble. Yeah, have to check to be sure. Here it is. Okay. So we follow the lead. Here it is. Go down to chloride. It's insoluble. So that one's insoluble. Potassium chloride, that's soluble. Silver chloride is insoluble. And you can verify that by just checking the chart. Lead sulfate, I'm pretty sure that was insoluble. Yeah, sulfate's insoluble. Potassium salts are all soluble. And then silver sulfate. Yeah, consider that before. Silver sulfate, that's insoluble. Okay. Lead phosphate, I'm pretty sure that's insoluble. Yeah. And silver phosphate. So that's insoluble too. Okay. So that's the most efficient way to decide solubility if you just have a mixture of ions like that. Just set up your chart. You know that cations are not going to interact with each other. So you put them on one side, anions on the other, and just match them up. Because once they're in solution, they have a chance to interact. Right? If they're all in solution to start with, then you can tell that when they interact, what are they going to do? Okay? Now this one says 5 different solid forms. I say 6 forms. They say chloride, sulfate, phosphate. Okay, they got that one right. Of course, they're naming the compounds and writing them out. That's okay. Once you get this done, then you can write those out. Silver chloride, yeah. Silver phosphate. Silver sulfate is supposed to be insoluble too. Unless it's considering silver sulfate a slightly soluble. But I think they left that one out. In fact, these are my slides. I can doctor it if I want to. So the next time I show this slide, it's going to have that correction. Where it is. Here it is. So we need silver. What's the subscript on silver with sulfate? Silver is +1, sulfate is -2. So silver would be an Ag2. So, okay. All right. Okay, so this is what I showed you earlier. That's the molecular equation, where you treat everything as if it's standalone molecule. And that's fine. When you write that equation, that's good, and it's easier to balance equations that way. So this is where you balance your equation. You write it this way. Once you get it balanced, then you bust it up into ions. And it needs to be balanced ahead of time, because if this is K2CrO4, then you know that 2 potassium ions come out for every molecule, for every one of these. So that makes the complete ionic equation, correct writing the complete ionic equation possible. Then you take the spectator ions, cancel them out, and you get your net ionic equation. That's the meat of the reaction. And it's the meat of the reaction because it forms a solid. Now, what would the net ionic equation look like? It's just, what if? If you did not produce a solid, you wouldn't have a net ionic equation, because everybody's spectators, right? You put sodium chloride and potassium chloride together. They go into solution, they stay in solution.
How can you tell it makes a solid?
You look at the chart. Yeah. Okay. Let's see. How are we doing on time? I'm going to have to skip this one. And move on to, you can study that on your own. You'll find that this is the molecular, this is the complete ionic. Once you get this one written, you can bust it up. And then you just subtract out the spectators. All right, so what happens when we put an acid in solution? Well, at least one of the hydrogens dissociates. Right? For strong acids, like this one, hydrochloric acid, complete dissociation in aqueous solution. Nitric acid, same. Sulfuric acid is diprotic. It has 2 acidic protons, but only the first one is strong. So when you put in this solution, you get one proton plus the hydrogen sulfate ion. Right? But it's still considered a strong acid because this step is complete dissociation. Okay? So that's what happens when they go into solution. You get those individual ions. And that's why if you put one of these strong acids in water, it will conduct electricity. So this acid is a strong electrolyte. Before, our example of electrolyte was sodium chloride. But in this case, the ions are that proton and that chloride ion. But it's still an electrolyte. Now, when you put a base in solution, a strong base, you get sodium separated from hydroxyl. Okay. Potassium from hydroxyl. Complete dissociation. Those are strong bases because they completely dissociate. That's the concept. Strong means dissociation. Strong doesn't necessarily mean a corrosive. In other words, the solution of that, stick your hand in it and it eats your hand off. It's a different concept. In chemistry, strong means complete dissociation. Now, corrosion, you can get corrosion from a weak acid if the concentration is high enough. Right? All you have to do is have enough protons in there to make it a very strong acid, and then it will eat your hand off. The acetic acid before, mostly like that. Right? So if you only have like 0.01 molar of that, then this dissociation is going to be just a tinkle. Like if you have a cut on your finger, you'll feel it. Or 5% vinegar, right? You can chug that with no harm. But if you have glacial acetic acid, which is the commercial term for 100% acetic acid, that still only partially dissociates. It's still a weak acid. But at 100%, it produces a lot of those. You stick your hand in glacial acetic acid and it will eat it off. Okay? So I'm just trying to make the point between what we commonly think of as strong is not chemistry strong. Strong is dissociation. What we normally think of as strong is corrosion. How effective is it at corrosion? Right? This is a strong corrosive. This is a weak corrosive. This is a weak acid. That's a weak acid. Okay? That's the point I'm making. Okay. So, when we get to the discussion of acids and bases, I think we're going to do that, aren't we? Chemical quantities, solution. Well, maybe not. Oh, yeah, toward the end. We'll get into this a little more detail. But when water is pure, there's nothing there but water, what it will do is it will dissociate into those ions. Only slightly, so it's very, very weak, but it does dissociate. So what does that say? Well, since it's very weakly in that direction, right, like that, most like this, that means it wants to be here. So whenever you have hydrogen ions and hydroxyl ions in solution, they attract to one another and they form that. So that's another driving force for a chemical reaction, formation of water. Because the attraction is so strong, If you produce these in a reaction, it will form water and drive the reaction that direction. Okay, that's why acid-base reactions are driven. Because an acid, use an example. Say an acid like that, plus a base like this. So what do you have here? In solution, they're both strong. So you have hydrogen ions, chloride ions, sodium ions, hydroxide ions. So you just double replacement. So this interacts with that. And this interacts with that very strongly to produce water. That's why the reaction is driven that direction, because it produces this. So this is a case where you don't form a solid, but the reaction is driven by the net ionic equation. So what's the complete ionic equation of that acid-base reaction? This and that. Right? They're separate ions in solution. Right? But when they interact, you get these ions plus this. Right? So where are the spectators? There, 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 there. So the net ionic equation for an acid-base reaction happens to always be this and this yields that. Every acid-base reaction is net ionic that. Protons plus hydroxyls make water. Okay, let's see here. That was a discussion. That was just what I was talking about. When you get these reacting together, there's your net ionic equation every time for an acid-base reaction. Other types of reactions. Right. Actually, it would be a very good idea, almost closely akin to an order. Take that review document. I did hand one of those out, didn't I? Take that review document and go through it. At least, you know, if you're limited by time, just take every other one, like all the odds, you know, so that you'll see some of the stuff that might show up on an exam, for instance. And you get exposure to the types of reactions. I'm not sure yet how complete that exposure is given to you in the homework problems. I assume it does a little bit, otherwise I wouldn't have done it. But so far we've done precipitation reaction, we've done acid-base reaction, okay. How to recognize those. Now oxidation reduction reaction. So when you have an oxidation reduction reaction, reduction, forget. There you go. That's how you remember what oxidation reduction is. Okay. Oxidation is loss, and we're referring to electrons. Loss of electrons is oxidation. Reduction, you can probably fill this one in. Reduction is gain of electrons. Okay. Oil rig tells you if you need a mnemonic to go back to. Oxidation is loss of electrons, reduction is gain. So if you can demonstrate a loss of electrons, actually they always occur in pairs. In a chemical reaction, you cannot have a loss without a gain. Right? Electrons got to go someplace, right? It doesn't just sit out there. The only place electrons sit out there is on a Van de Graaff generator. I remember as a kid in grade school, living in Oak Ridge, Tennessee. At that time, it had the highest concentration of PhD scientists and engineers in the country. So our public school systems were top. They were the best you could get. And one of the things we did was we went on field trips. And they had this museum type thing where they demonstrated things. And one of them was a demonstration of a Van de Graaff generator. Everybody knows what that is? It's that thing with a tall tube and then a big bulb on top, silver bulb. It deposits electrons on that bulb here. So you get a distribution of charge, high density of electrons. So they pick a young blonde girl with long hair out of the group and say, okay, put your hands on the bulb and don't take them off. Keep them there until I tell you. So as long as she was holding on to that bulb, there wouldn't be a shock. But when they turned that generator on, the electrons collected up there and they went through her skin and into her hair. And electrons naturally leak from pointy surfaces, right? So they leak from the tips of her hair. So as the electrons collected on her hair, they repelled one another, and this little girl had hair standing out like that. It was hilarious. And then, of course, they shut it off, and then they allowed the charge to dissipate, and then she could take her hands off safely. If you take them off too soon, you get a huge shock, because they're developing volts in the neighborhood of 10, 20, 30,000 volts. Okay, so transfer of electrons. So in this case, when you react magnesium with oxygen, right? Magnesium's a solid, oxygen's a gas. You're going to get magnesium oxide, right? And you're going to need 2 here and 2 here to balance it. But what happens? Well, over here, magnesium is a metal. It's an element. It has no charge, right? Right, remember the 4 positions around your symbol? That's where you put the charge. There's no charge on magnesium. There's no charge on oxygen either. But when we form a compound, this is an ionic compound, magnesium has a 2+ charge because it comes from here, second group. Oxygen is -2, -1, -2. So it has a charge of 2-. What happened? In order to develop a charge, you have to transfer electrons. Right? If you add electrons, the imbalance is toward the negative. If you subtract electrons, the imbalance is toward the positive. So that means in order to go from here to here, what did we do? Oxidation is loss. Loss 2 electrons per magnesium, right? This just talks about the 1 magnesium, 0 to 2+, but we have 2 of them, right? So if we have 2 magnesiums times 2 equals 4 electrons were lost by those 2 magnesiums. Where did they go? They have to go somewhere. Gain 2 electrons per oxygen. But we have 2 oxygens, 4 electrons. So the transfer of the loss of 4 electrons is balanced by the gain of 4 electrons. That's an oxidation reduction reaction. Okay? Now, if you're in a hurry on a test, you may not have time to do all that. You may have to, but here's a trick. If you have on one side of the equation an element, right, like this, on the other side, your element is in a compound. That's oxidation reduction, automatically. If the question is it oxidation reduction or not? True, false. Well, I don't give true, false, but if you have to select from a list. and say, what is this reaction? You just say, that's an element, that's a compound with that element, it's oxidation reduction, go on your way. Okay? This is another example, I think. Aluminum and, oh, that's a good one. Aluminum metal and Fe2O3. Right? So that would be iron-free oxide. And what does it yield? Well, it yields iron solid plus aluminum oxide, Al2O3. So you see, element in a compound, or element coming from a compound. That's oxidation reduction. Now this particular reaction generates a lot of heat. That's called thermite. It takes a lot of heat to get it started. You know, you got to start it with, I don't know, what are they starting with? Torches, or not blasting caps, but some sort of incendiary. Gets it started. But once it gets going, I mean, it is, you can't even look at it. They use them on joining railroad, because it produces this iron as a product, and that welds the steel together.
We use that underwater welding too.
Okay. Yeah, it produces so much heat, not even water can quench it, right? Okay, but that's an oxidation reduction reaction. A metal non-metal reaction. Yeah, there's that rule. Metal non-metal. Anytime you put a metal and a non-metal together, that's an oxidation reduction. Like sodium metal and chlorine gas makes sodium chloride. Or the other thing is, if you have an element on one side, it's in a compound on the other. Right? Even if it's non-ionic, say you have hydrogen gas and oxygen gas makes water. In the space shuttle engines, right? Liquid hydrogen, liquid oxygen, they mix them in the space shuttle engine. Well, they used to before they shut the program down. But it forms water and a lot of heat. It generates high energy output, accelerates the vapors out the back at such high velocity, they give you a nice big push. But that is an oxidation reduction too. Element, compound. Element, compound. Transfer of electrons. So there are your driving forces for reactions. We didn't cover formation of a gas, but it too is a driving force for a reaction. There are examples in your review document that I want you to take a look at. Back here, let's say, around page 32 or thereabouts, you have reactions and you want to classify them. You know, is it oxidation reduction? Is it precipitation? Is it acid-base? Right? The thing is, one reaction can be more than one type. Right? So you have to consider the reaction plus your selections. Right? This is multiple choice. So look at your selections and say, which one of these fit that reaction? Could be more than one. So look at the key, and the key will guide you through those that tend to be tricky. Okay, formation of gas. Okay, formation of gas can be an oxidation reduction. It could be classified as a single replacement. So what do we mean by single replacement? Here's an example. Zinc metal, hydrochloric acid. Have you ever, maybe you've never done that. It's fun. You just take pure zinc metal and put it in hydrochloric acid of sufficient concentration. And pretty soon you start forming, see gas bubbles. those gas bubbles are hydrogen gas. So if you collect them, like you have a container inverted over it, you collect that gas, then you can take a lighted ember and put it in there and you go, it'll pop. But in the process, you've taken a metal and made a compound out of it, element to compound, that's oxidation reduction, right? But it's also single replacement because what did it do? Zinc replaced the hydrogen. See, kick the hydrogen out. Now zinc and chlorine are together, and hydrogen's off by itself. That's a single replacement, as opposed to the double replacement I showed you earlier with precipitation formation. Here's a flow chart that may be useful. The different chemical reactions could be precipitation, which was also classified as a double replacement. Or it could be acid-base. Right? These two, 99.9% of the time, let me put it that way, I hedge my bet, will not be oxidation reduction. Oxidation reduction will be obvious. And then oxidation reduction can be something else. The one we haven't discussed yet is combustion. It's a special kind of oxidation reduction. So here we go. This is a perfect example. Hydrogen plus oxygen. You have to have that for a combustion reaction. So if you see oxygen element here, all by itself, reacting with something, it's a combustion. But it's also oxidation reduction. Okay, so there's an example, can be both. Oops. Natural gas on your stove, that's a combustion reaction. It's also oxidation reduction. Because the primary compound in natural gas is methane, CH4. Other types of reactions, what do we mean by synthesis? Where you take elements or simpler compounds, put them together and make something more complex. That's a synthesis. Go back the other direction, that's a decomposition. So you can get 2 for 1 out of that one. There's your decomposition, right? So we can take water, put a little acid in it, drop a 9-volt battery in it, and one electrode will make gas and the other electrode will make gas. One's producing oxygen, the other one's producing hydrogen. So we're decomposing water into its elements. This is more complete, right? So you can go from oxidation reduction to combustion. Could be combustion, could be synthesis, could be decomposition. But anytime you have these types of reactions, they involve transfer of electrons. Let's see. So this reaction is all of the above: combustion, synthesis, oxidation reduction. So there's a trifecta. Let's see, am I close to finish? I think that's the last slide, isn't it? Yep. So we're done. Y'all wake up now. I know how it is. I used to be a student one time. Falling asleep in class.
I try to say I haven't done that in any class yet. Not even history.
Yeah. Or even sitting in class and freezing to death, right?
If even for 3 seconds,
Most of my classes were in big lecture halls. We had like 60, 70, 80, 120 students at once. It was very impersonal.
yeah, I could see a lot of them waking off, falling asleep, and no one knowing.
Okay, let's stop this thing and start the conversion. Do you still want to talk about that problem?
I need to do some, I'm pretty sure it's probably
Okay. That's fine. Yeah, next time we meet, we'll do a review. Yep. Yes.
let's see.